So far we have completed representing each and every node individual type, as well as we have also uh, written the class for representing singly linked list in our programmatic implementation, right? Now we have everything in place. Now let's get on with implementing the very first functionality, that is push functionality on a singly linked list. So generally what exactly this push functionality does is it will basically take the new value from the user and it will basically try to create a new node of type node that we have defined, and it will make sure that it is inserting that node at the end of the singly linked list. That means the end is exactly at the tail node, right? Because the tail value inside the singly linked list basically represents the very last node that we have, and obviously we have the tail node access as well inside the singly linked list representation that we are maintaining. So as part of the push operation, whatever the new node object that we create with the value that we take from the user, and it will make sure that it is adding that new node at the end of the singly linked list. But remember that, because we are adding a new node at the end of the singly linked list, whatever the tail node that we had previously, right, that will no longer be the new tail node. Whatever the new node that we have added will become the new tail node of the singly linked list. That is something that you have to remember. That means whatever the tail node that we are maintaining inside our singly linked list representation, right, we have to update it with the newly added node. Okay, so that is the simple definition. So what exactly we will do, we will take the value from the user and we will create the new node object of type node that we have defined, and we will make sure that we are adding it at the end of the singly linked list. So what all are the different cases that could come while implementing the push operation, right? So basically remember that, whenever you are adding a new value or new node into the singly linked list, right, there could be two scenarios. The first scenario is to check if the singly linked list is empty, and the second check would be to check if the singly linked list is not empty. Whereas when you are trying to remove the value from the singly linked list, right, then there will be three scenarios. First scenario is basically the singly linked list can be empty, and the second scenario is basically where we have only one node, and the third scenario is basically where we have more than one node inside the singly linked list representation. Since here we are introducing a new value onto the singly linked list, right, so obviously the first case would be to check if the singly linked list is empty, right? Obviously when the singly linked list is empty, whatever the head node and tail node that we are maintaining, right, in the case of Java or JavaScript representation, we are maintaining null value in it. Otherwise, if we are trying to do it Python based implementation, right, in that case we are storing none in it. In both head and tail we have null. In the case of Python implementation we have none. Similarly inside the length we are having 0. So whatever the new value that I am adding into the singly linked list, that will be the only node that will be present inside the singly linked list, right? That means whatever the node that we have added will become the head node as well as the tail node. So we have to make sure that we are updating the head with the new node that we have added. Similarly, tail node also we have to update it with the new node that we are adding, because we have only one node in the singly linked list. That means that itself is the head node and tail node. That's why inside the head value and the tail value we are maintaining, we have to make sure that the reference of new node is getting updated inside that. Similarly, since we are adding a new value into the singly linked list, we need to increment the length by length plus 1. Okay, so that is the first scenario where head and tail were not there. That means the singly linked list is empty. Now let's try to understand the second scenario where we have a non-empty singly linked list. So non-empty singly linked list case is what we have here, right? Obviously here we have some number of nodes already available inside the singly linked list, and we have the head node and we have also have the tail node. So each and every node has some value in it. Let's say 10, let's say k, let's say true or something like that. Now let's just say I want to add or I want to push the value, let's say code, onto the singly linked list. So what I will do is, we already have the reference of the head tail node, right? So from the tail node, the existing next pointer in the tail is, at this point of time it is null if you are doing Java or JavaScript based implementation, if it is none if you are following the Python based implementation. So here we will basically create a object, node object with the value code, and we basically update the reference of the existing tails next to newly created node. That means in the existing tail node we have the reference of the newly created node as well. So we have adjusted the next pointer of the existing tail, and obviously the next on the newly added node is, obviously it is empty. Now this, whatever the true node that was there, will no longer be the tail node of the singly linked list, right? So what we have to do, we have to update the tail node to the newly added node, that is code. That means whatever the tail reference that we are maintaining inside the singly linked list, right, it should be updated with the new node that we are adding. In this case we will not do anything with the head because we had certain number of values inside the singly linked list. That means head is somewhere but the tail is somewhere, and to that tail node we are adding a new node as part of the push functionality. So we will not do any changes to the head node, we will simply update the tail node with the newly added node, and we will also increment the length by 1. Okay, in this way we are keeping consistency in the tail node because we are adding a new value into the singly linked list after the end, and we are adding a new node into the singly linked list, right? That's why we are incrementing the length by 1. So that is how we are maintaining the consistency across the variables we are maintaining inside the singly linked list representation. Okay, now according to the algorithm that we have discussed, right, for various cases on a push operation, now let's try to write the pseudocode for the same. So inside the pseudocode, what exactly we are doing, we basically define a function called push function, and this function will basically take the new value from the user. So for as part of the first step, we have already defined the node class, right? So we basically create the node object with the value that user has passed, be it empty singly linked list, be it non-empty singly linked list, we have to have the object of node first. Based on that, based on whether the singly linked list is empty or based on the singly linked list is not empty, we will try to perform the operation, right? So after creating the object, what we will do is we will check if singly linked list is empty. How we will check? If you are doing Java or JavaScript implementation, right, inside the head, when we created the object of singly linked list, we have assigned null, and inside the tail also we have assigned null, and inside the length we have assigned 0. If you are following Python based implementation, right, inside the head node, null equivalent is none, right? So we have defined head with none. Similarly, we have defined tail also with none, and length we are maintaining 0. Now if the singly linked list is empty, in the case of Java and JavaScript implementations, head and tail will be pointing to null and the length of singly linked list will be 0. So based on that, we will be able to decide if the singly linked list is empty or not. Now anyway, that algorithm I have already explained, just that I am trying to give much more context here. So if at all, if the singly linked list is empty, right, whatever the new node object that we have created will be the head node. So head node, we will update it with the new node object. Similarly, since that is the only one node, we will make sure that tail node also is getting updated with the new node object that we have created. And after that, we have to increment the length by 1. Increment length by 1. In the end, we will simply return the node that we have added. That is, whatever the new node object that we have created, we will return that. So this is the case where the singly linked list is empty. If at all, if the singly linked list is not empty, right, that means it is not empty. In the case of non-empty singly linked list, we already had the reference of the tail node inside the singly linked list containing some number of values. So inside the tail node, obviously the next reference was empty. So we have to make sure that since we are adding a new node, this node's reference should be present as part of the existing tail node, right? So first we will read the tail node. Okay, so in this tail node we will basically update the next to new node. Okay, that means we are adding this object reference into the existing tail node. After updating, we have successfully added the new node into the singly linked list, but the tail node is still pointing to the old last node that we have inside the singly linked list. So the tail node should be updated to the very last node we have in the singly linked list. To do that, what we will do is we will simply update the tail node to the new node object that we have added. Similarly, in this case also, we have to increment the length by 1. In the end, we will simply return new node object. Okay, so this is the pseudocode for implementing the push functionality on a singly linked list. So remember that there will be two cases. One will be empty singly linked list and the other will be non-empty singly linked list. Okay, so that is how we perform the push functionality, and let's go ahead and let's try to implement it programmatically as well. So I'm right now inside the singly linked list.js file that we have written, and we validated whether we are able to create an empty singly linked list or not, right? In that only, I'll try to add a function called push. Okay, this push function will basically take the value that user wants to add it at the end of the singly linked list. So as part of the first step, what I will do is I'll simply create the node that I want to insert at the end of the singly linked list with the value that user has passed. So to create that node, first I will have to import the node class. To import it, what I will do is I'll simply do const equal to require of. We need to import it from the node file that we have already written here. So the class name is node and we are simply doing module.exports of node, right? So we will be able to import it here like this. Okay, now what I will do with the value that user has passed, I will try to create a new node with that. So let's say const new node equal to new node, and we need to pass the value to the node class that we have created. As part of the constructor, we are taking the value. So when we try to create the object of node, we need to pass the value that I want to store as part of the node that I'm creating. So for that, I'm going to pass the value, okay, that user has passed. Now, if you remember the pseudocode that we have discussed clearly, there are two scenarios, right? One, the singly linked list on which we are trying to push is empty, or the singly linked list that we are trying to perform this push operation is non-empty. So if it is empty singly linked list, how will we able to identify? In the case of empty singly linked list, the head and the tail are null and the length is 0. So based on either of these checks, we will be able to identify if the singly linked list is empty or not. So what I will do, I'll simply if this dot head. So current object's singly linked list head node is, if it is null, what I will do, in the case of empty singly linked list, whatever the new node that we are adding, it itself is like a head node as well as tail node. So we need to update the head node and tail node also to the newly created node. So to update this dot head, which will basically have the reference of the head node in the linked list, this we are updating to the new node that we have added. Along with this, the tail node reference which we have inside the this dot tail will basically get us the tail node reference, right? So this dot tail also we are updating it to the new node. Okay, this is a case where we are trying to perform push operation on a empty singly linked list. Okay, but what if we are trying to perform the push operation on a non-empty singly linked list, right? To do so, what we will do, we will add the new node to the existing tail node in the case of non-empty singly linked list. So we have the current tail node, we have the newly added node. In this case, from the current node's next pointer should be updated with the newly added node, right? So that case we need to handle. So for that, we will simply do this dot tail, which will get us the current tail node of the singly linked list, and this tail is nothing but the node, right, that we have stored in some previous operations. So this node will have the next pointer. So next equal to new node that we have created. But once we have adjusted the next pointer from the current tail node to the newly added node. But in the case of push operation, we are trying to add the new node at the end of the singly linked list. That means whatever the tail node we had previously before adding the new node is no longer the tail node. Whatever the node that we have added right now will be the tail node. So we need to update the tail node to the new node that we have added. So this dot tail equal to new node that we have created. Okay, we have honored the two cases where first case is when we are trying to perform push operation on an empty singly linked list, and the second operation is when we are trying to perform the push operation on a non-empty singly linked list. If you observe both these cases, right, irrespective of whether the singly linked list is empty or non-empty, we are trying to add a new node into singly linked list. That means we are incrementing the length by 1. So we need to keep track of the length also in the length variable, right? So to keep track of that, this dot length, I'm incrementing it by 1. So this dot length plus 1. Okay, in the end, as part of this push functionality, we want to return the new node that we have added, which is available at the tail variable, or else you can simply return the new node also. So we will simply do return this dot tail, or you can simply do return new node itself, because this new node itself is tail node in the case of empty singly linked list or non-empty singly linked list based on the assignment you can see on the implementation. Okay, this is how the push operation is implemented. Now let's try to call this push function and validate the result. So let me just remove these log statements. Here we have anyway created the object of singly linked list, right? So let me call the push function push, and I should be able to store any type of value in the singly linked list. Don't forget that. So if I do sll dot push off, let's say I want to store some string, let's say codingpal dot org. Okay, or else similarly I want to say I want to store sll dot push off, let's say I want to store some boolean value. Okay, irrespective of the data type of the value that you are trying to store, it should be able to store it as part of the node. Why? Because singly linked list is a heterogeneous data structure. That means it should store any type of the value as part of the specific node. Okay, at this point of time, don't worry about printing the values inside the singly linked list and validating whether the implementation that we have done is actually storing the value 10 codingpal.org and true in it or not. In the next functionality that we are going to implement, we will perform the traverse function, which will basically read and print the values from head node till the tail node. Okay, in the next function we will actually validate if it is actually able to store the values, and if we are able to successfully update the tail node and all, we will be validating in the next traverse functionality. Now we have written the programmatic implementation of push functionality as well, right? Now let's just try to understand the time complexity and space complexity involved in performing the push functionality on a singly linked list. To handle the both scenarios, even if we have n number of nodes in the singly linked list, or even if the singly linked list is empty, what exactly we are doing? First step, we are basically creating the object of the new node with the value that user has passed, right? So obviously for that creation of object, we will not take more than 1 unit of time. Similarly, in the case where we don't have the nodes at all inside the singly linked list, right? Exactly, we are simply updating the head node and tail node with the new node that we are creating. Since these are simple assignment operations, and incrementing the length also is a simple assignment operation, right? These operations will take 1 unit of time itself. As a result, when we don't have any nodes inside the singly linked list, the time complexity will be order of 1 only. Similarly, even if we take the case where we have certain number of nodes inside the singly linked list, that means the singly linked list is not empty, right? In that case also, we are maintaining the reference of the tail node in our singly linked list representation. That means inside that class that we are maintaining for singly linked list, we can directly read the tail node. That read operation is obviously is going to take 1 unit of time itself, and after that we are updating the next reference of the current tail node with the new node that we are adding. So obviously this is also a simple assignment operation, and it will take only constant amount of time. In the end, just like how we handled updated the tail reference and incremented the length by 1, right? Then these are also simple assignment operations, so these will also take constant amount of time. So as a result, even if you take the case where we have certain number of nodes available inside the singly linked list, the time complexity will be order of 1 only. And if you take the space complexity, obviously the only space that we are consuming is basically to create the new node with the value that user has passed. Obviously we can't skip that node object creation, right? And we won't consider that as a memory consumed by the algorithm that we are using for performing the push operation. So obviously the memory that is consumed by creation of node object will also be constant. And if you take the case where we don't have any nodes inside the singly linked list, we are simply updating the reference of the head that we have already have inside the singly linked list and tail with the new node. So these will obviously simple assignment operations, and they will not consume any more memory internally, right? As a result, overall memory consumption in the case where the singly linked list is empty, right, it will be constant. That is, it is order of 1 only. Similarly, if you take the case where the singly linked list is not empty also, we are not consuming any memory, we are simply performing the assignment operations, and these assignment operations will not take more than a unit of memory, right? That's why in this case also the space complexity will still remain order of 1 only. Okay, so that is all with respect to implementing the push functionality on a singly linked list. In the next video, let's talk about the pop functionality on a singly linked list, where we try to delete the very last node we have inside the singly linked list.